All right, welcome everyone. Today we are going to be studying greedy algorithms and matroids. It's a fascinating connection. I think you're going to enjoy it. Okay, so let's begin with a quick introduction recap of greedy method. Greedy method is a technique to build a complete solution by making a sequence of best selection steps. Now the selection depends upon the actual problem, but the focus is simply on what's best from this point. And we have studied many different kinds of greedy algorithms, but one of the greedy algorithms that we did study was the Kruskal's greedy algorithm for the minimum weight spanning tree. And there's a separate video on its own. Feel free to watch that first if you haven't seen that yet, to have a good understanding of how that greedy algorithm operates. And that particular video doesn't mention matroids. That's what we're going to cover today. The way this algorithm works is very simple. It sorts the edges in the increasing order weight and keep selecting each edge that does not cause a cycle. So there's that focus of being able to do the best selection from this point. Okay. But today we are going to be studying the concept of matroids. Matroids is a great concept that we study in the subfield of discrete mathematics, also under the field of combinatorics. So before we study matroids, let's understand what is a subset system. A subset system is simply a set E of any elements together with a set of subsets of E. So think of the power set of E, but here we're not thinking about all the set of subsets, but just with a smaller set of subsets that we'll refer to as I. I is sometimes called the independent set. And for that selected set of subsets, that I is closed under inclusion. Closed under inclusion simply means that if you take an element of I, then you take a subset of that. So here that element is Y. So if Y is contained in I and you take a subset X of that Y, then X is also contained in I. So this is simply the hereditary property, which simply means that a subset of a valid solution is a valid solution. Okay. Or in other words, a subset of an independent set is an independent set. So that's really all that this particular property says, and that's all that the subset system actually says. Even though sometimes maybe the language may look a little bit like a jargon, but actually it's a very simple concept. So again, a subset system is a set E together with a set of subsets of E that we refer to as I. I is that set of subsets of E, such that I is closed under inclusion. That means if you have a Y, which is a subset of E, so if that Y is in I, then a subset of Y is also going to be inside I. In other words, if Y is independent, then subset of Y is also independent. Now this independent set is not to be confused with what is an independent set in the context of graph theory, even though the fact that they're referred to as independent there's some analogy between them, but this is not to be confused with that at the moment. At this moment, we're just talking about a subset system, and I is referred to as the independent set here, or rather the set of independent sets. Each subset like X or Y is an independent set. Okay. A matroid is a specific kind of a subset system. Not all subset systems are matroid, but all matroids are subset systems, such that if they satisfy the exchange property. Exchange property essentially just means that if you have two sets in I, like suppose I1 and I2, I1 has fewer elements than I2, then there should be some element in I2 that we can add that doesn't already exist in I1, that we can add to I1 such that I1 still remains an independent set. Essentially, in common English, we can refer to it as an augmentation property or the independent set exchange property. That basically just means that if a larger solution exists, we should be able to add something to the current solution, which is what we also see in the concept of greedy algorithms when we say that to build the solution one step at a time. And that's what the concept of matroid here is. Now, if we go back to the basic properties of optimal greedy algorithms, they have these two common properties. One property is that the optimal substructure property. A problem has an optimal substructure if the optimal solution to the problem contains within it optimal solutions to the subproblems. Again, the language looks very much of a jargon, but simply put, what it says is that if you take a problem, you come up with a solution, then look at a part of a solution. That part of the solution will be the optimal solution for that part of the problem. Okay, that's what the optimal substructure property says. And for the greedy algorithms to work, it also has to have the greedy choice property. That means that if the local greedy choice is made, then the optimal solution using the choice is still possible. If we go back one slide, we can start to see the analogy between the augmentation property and the greedy choice property. And that really brings us to the big result. The big result is that the greedy algorithms and matroids actually go hand in hand. More specifically, for any subset system EI is that subset system, the greedy algorithm will solve the optimization problem for EI if and only if EI is a matroid. So if you think the greedy algorithm will solve it, then effectively you are saying that EI is a matroid, vice versa. If you say EI is a matroid, that means the greedy algorithm will solve it. This may appear to be theoretical, but let's look at very, very, very practical way to look at this. So consider a graph here. So we think of the sets of edges. We're given the set of edges of a graph and a set of forests. So forest is just a set of edges that doesn't have a cycle. Normally we think of the word tree, but think of many different trees spread out. That's a forest. So the first clear observation we can make is that a subset of a forest is also a forest. That simply means that this satisfies the hereditary property. So clearly this is a subset system. A subset of a forest is also a forest. So if you have the definition of a valid solution as it has to be a forest, then the subset of that forest will also be a forest. So that satisfies the hereditary property. Now consider two forests, F1 and F2. If F1 has less edges than F2, then you can certainly add an edge from F2 to F1 such that F1 prime will still be a forest. So we also see that the set of forests is the system of forests is a matroid. So that's an observation rather that's just an example of matroid. The set of forests in a graph forms a matroid. It has a specific name. It is known as the graphic matroid. Okay. So here we're just giving you an example of a matroid. Now I want you to bring you to a reminder that the Kruskal's greedy algorithm does solve the minimum spanning tree problem optimally by building that forest one step at a time. So here I'm trying to invite you to make a connection between this slide here, that the system of forests is a matroid, and yes, a greedy algorithm actually solves it. Okay, so there's that connection. Now let's go to an example of a non-matroid. So if that's a matroid, what's a non-matroid? Now let's take another example still within graph theory. And let's say the set of clicks. A click is a set of vertices that are all connected to each other. Now clearly the subset of click is also a click. It's a smaller click, but it's also a click. So think about you have a click with 7 vertices. That's referred to as K7. But if you have a click with, and you only take 6 of those 7 vertices, that will also be a click, even though it'll have smaller vertices. So click is definitely a subset system. However, now think you have a click over here that has maybe some vertices, a click over here that has more vertices. But now it's not guaranteed that you can add a vertex from here to here and this will become a click. Maybe these vertices are not connected to these vertices at all. So you cannot add anything to the first click here. So therefore, the click system does not have the augmentation property. It's not a matroid. And now I want to bring you to another observation here, a reminder that we do not have any known optimal time algorithm, any known optimal algorithm for click problem that runs in polynomial time. In fact, we will see this in our NP completeness part of the series, that this is an NP complete problem. So again, I'm trying to suggest to you that when you have a non-matroid, there's no easy greedy algorithm here. In fact, there's no known optimal algorithm, but specifically, let's say we limit ourselves to greedy algorithm. No greedy algorithm is known to us that finds that that can solve the click problem. In fact, the observation here suggesting that a greedy algorithm will never be able to solve it. If some other algorithm is found, then that will kind of solve the P is equal to NP kind of problem as well. But there you have the two connections here. So there's a quick summary for you. Greedy algorithms and matroids, it's a fascinating link between them. They are really two sides of the same coin. But the big result here for us today, for any subset system EI, the greedy algorithm solves the optimization problem for EI if and only if EI is a matroid. That's all I have for you. Normally we think about greedy algorithms and we don't think about this mathematical topic about the subset system and matroid, etc. But there you have it. I hope you have fun with it. Keep learning. Enjoy. Okay.